NASA has just reported that its Voyager 1 spacecraft, the most distant man-made object in space, once again is transmitting useful data from space back to Earth. This is a tremendous recovery from receiving unintelligible signals from the spacecraft for months. As much as humanity has explored the solar system in unprecedented detail, new findings continue to amaze us. We believed the solar system's planet count was finalized for years until new findings proved us wrong. The Voyager probes, among others, have ventured beyond the boundary, offering data that never fails to amaze scientists. One of the most intriguing findings is that our entire solar system, including the distant Oort cloud about a light-year from the Sun, is contained within a colossal cosmic bubble. The giant formation is approximately 1,000 light-years in diameter and strangely places the Sun near its center. But what does this do for our understanding of the universe? What exactly did we find out when the Voyager spacecraft crossed the boundary of the solar system? Could we be inside a gigantic space bubble? And what does this discovery do for our understanding of solar system dynamics? Let's see. Voyager 1 was launched from Cape Canaveral, Florida, on September 5, 1977, some weeks after the departure of its twin, Voyager 2, which was launched on August 20th. Designed to conduct a 5-year survey of the outer planets, the duo have far exceeded expectations, sending data back to Earth for more than 4 decades as they explored deeper into interstellar space. Their success depended on a rare alignment of the planets, which occurs only every 176 years, to allow gravity-assisted flybys between the planets, saving fuel. Although Voyager 2 launched first, Voyager 1 entered Jupiter and Saturn space first. While Voyager 2 made the grand tour to Uranus and Neptune too. The vast quantities of data collected by the Voyager missions have contributed immensely to our knowledge of the outer solar system. These have been incorporated into scientific literature, education, and popular culture. Both spacecraft also carry an extraterrestrial message, a gold record containing sounds and music of the Earth intended for any would-be extraterrestrial society. Voyager 1 stands at 14.9 billion miles from Earth, approximately 158 times the distance between Earth and the Sun, as of January 2024, which makes it the most distant human-made object. Voyager 2 entered interstellar space in November 2018, following Voyager 1's historic crossing over in August 2012. It required confirmation from data obtained by Voyager 1's plasma wave instrument for NASA to determine that Voyager 1 had crossed over the heliosphere, the gigantic bubble of charged solar plasma particles. In April-May 2013, the spacecraft recorded a colossal solar eruption that caused electrons in space to oscillate. Scientists determined that electron density outside the heliosphere was much higher relative to inside the heliosphere, confirming that Voyager 1 had crossed into interstellar space. This observation gave evidence that whereas interstellar space is denser than spaces near the Sun, the outer boundary of the heliosphere is far less dense than expected. Examining this information, scientists concluded that Voyager 1 officially entered interstellar space on August 25, 2012. Voyager 2 soon followed in 2018, offering key validation of the structure of the heliosphere. Both spacecraft measured comparable densities of particles in interstellar space but also detected significant differences, raising new questions regarding the Sun's path through the galaxy. Voyager 2 measurements gave scientists a never-before-seen glimpse into the outer edge of the heliosphere, the heliopause. Though calm-looking from our planet, the Sun is an unpredictable, magnetic behemoth hurtling across the galaxy at 450,000 kilometers per hour. Its solar wind filaments of electrically charged gas tends to extend the Sun's magnetic field into space, eventually bumping into fragments of long-dead stars in the interstellar medium. When the two very different environments meet, they produce the heliosphere, a protected bubble around the solar system that stretches out about 11 billion miles from the Sun. This shield protects Earth and the other planets from harmful cosmic radiation. Without it, life such as we know it would be threatened from galactic peril. The heliopause is the distance from the Sun beyond which solar wind cannot hold back against the pressure of interstellar space, and the discovery of this border has implications that extend far beyond the capability to learn about not only our Sun, but other stars throughout the universe. Voyager 1's journey through the heliopause gave the first direct glimpse of this boundary to humans, although it was difficult to make sense of the data as its plasma instrument failed all the way back in 1980. Scientists found interstellar magnetic fields were 2 to 3 times stronger than predicted, or a much greater pressure from interstellar particles than previously believed. Fortunately, Voyager 2's fully functioning instruments made more detailed measurements as it entered and crossed the boundary. When Voyager 2 arrived at the heliopause, it took measurements of slowing, heating, and thickening plasma, a dramatic change that gave scientists an unprecedented look at this critical boundary. The interstellar plasma was found to be extremely hot, with temperatures above over 54,000 degrees Fahrenheit. But because this plasma is so tenuous, the temperature around the probes is very low. Voyager 2 confirmed that the heliopause is not a barrier but an open boundary. Voyager 1 observed multiple streams of interstellar particles piercing the heliosphere, like tree roots forcing their way through stone. Voyager 2 also detected a feeble trickle of low-energy particles out to over 100 million kilometers past the heliopause. The solar wind fell sharply as Voyager 1 reached the boundary, creating a ghostly hiatus. Voyager 2, though, encountered a transition layer in the solar wind, adding to the complexity of the heliosphere structure. These various experiences suggest a dynamic and asymmetric heliosphere whose true shape remains to be discovered. Some theorize it may be spherical, others a comet-like tail, or perhaps even a glass-like deformation under interstellar pressures. But perhaps we do not yet know the answer. Modern spacecraft, such as the high-speed New Horizons mission, won't make it to the heliopause. New Horizons will begin to lose power in the 2030s, still a billion miles away from the edge. This constraint has renewed interest in sending a next-generation interstellar mission, one that might explore the outer reaches of the solar system in more detail. With only 2 data points, from Voyager 1 and 2, we can't chart the entire shape or form of the heliosphere. More exploration is needed. The second amazing discovery was when Voyager 1 detected a persistent, low-pitched hum in interstellar space. Using its plasma wave instrument, the spacecraft measured oscillations due to solar activity. Even in their absence, a weak, constant signal persisted. The hum suggests that interstellar space, which on the surface looks empty, contains active but subdued plasma activity. By examining this hum, researchers can learn more about the density and structure of plasma outside our solar system and how it interacts with the solar wind. The Voyagers have revolutionized our understanding of space, unveiling the secret dynamics of solar and interstellar particles. Even information from decades past continue to influence our knowledge. For instance, a re-examination of Voyager 2's 1986 flyby of Uranus indicates that initial presumptions regarding the planet's magnetosphere may have been erroneous. A transient solar wind event will have compressed Uranus's magnetosphere during the flyby, pushing plasma out and causing scientists to presume the system was abnormally evacuated. These events only happen 4% of the time, so Voyager 2's encounter could have recorded an anomaly instead of the norm. This reanalysis suggests that Uranus's 5 biggest moons are likely to be geologically active and possibly have subsurface oceans. It also illuminates the planet's unusually powerful radiation belts, the second most powerful after Jupiter's. These discoveries highlight the importance of timing in space exploration and have ignited calls for a dedicated mission to Uranus. This is now a top priority in NASA's planetary science roadmap. Meanwhile, Voyager 1 remains in remarkably good shape. In October 2024, the spacecraft lost contact and ceased transmitting via its main X-band transmitter. Engineers quickly picked up a weak signal from its backup S-band transmitter, last used in 1981. This surprising revival most likely originated from Voyager's fault protection system, which is meant to conserve power and keep the spacecraft running. Capturing such a faint signal from over 15 billion miles away was no small feat, but NASA's Deep Space Network successfully confirmed the spacecraft's status. But the S-band system can't transmit high-resolution data, limiting the team from monitoring Voyager 1's health. The engineers are now evaluating whether they can safely restart the main transmitter. This incident showcases the mastermind foresight and resilience of the Voyager design, with redundant systems to maintain long-term survivability. But operating these systems is not straightforward. With a near 2-day round-trip delay in messages, every command has to be thought out and tested. What will become of it then? A million billion years from now, the Voyager probes will be cruising through the galaxy in silence. They'll long be inert with their instruments disabled, but they will continue to journey on, the most distant 50,000 light-years away from the Sun. Voyager 1 will leave behind the course towards star AC plus 793888, and Voyager 2 moves in the direction of Ross 248 in the Andromeda constellation. These stars will not intercept probes for tens of thousands of years. However, the most important discovery in the next few years might be something we have yet to dream of. Curious? Take a stab in the dark, you might be closer than you think. If this ride through Voyager 2's history has intrigued you, don't forget to like, subscribe, and turn on notifications for more. Thanks for along for the ride, and catch you soon.